Hi there. In this video, we're going to be looking at an application of dot product, and it is to compute work. Okay, so let's just look at this example, and we'll talk about what all this is. A father is pulling his son on a sled at an angle of 20 degrees with the horizontal, with a force of 25 pounds. He pulls the sled in a straight path of 50 feet. How much work was done by the man pulling the sled? Okay, so what is work? Well, work, we know from physics that work is force times distance. Work is force times distance. So if I were to apply a force of, say, 5 newtons on a sled or a wagon or something like this, or just pushing a refrigerator along the path, and I was going to do it over a distance of 10 meters, then for the work done would be the force of 5 newtons, so it would be 5 newtons multiplied by the distance, 10 meters, and of course the answer there would be 50 Newton meters. Newton meters, we often write, instead of that we write a J for joules. Joules are named after the English physicist from the 19th century, James Prescott Joule. He studied heat and its relationship to work, and he studied the conservation of energy. All right, so that is the metric units for measuring work. All right, well, the problem that we're dealing with, though, is that we've got a force not being applied in the same direction as the motion. So what we just talked about doesn't quite work, excuse the pun, because in the picture that I drew, the force was being applied in the direction of motion. So something a little bit different is going on here. Okay, so let's think about what we would do in this scenario. Well, let's think about the case where we're pulling something, this box, and we're tugging up at it at this angle, all right? And suppose it's a 5 Newton force up at this angle, and again, I'm going to displace this object 10 meters, okay? And I want to know how much work is done now. So we're not pulling in the direction of the motion, we're pulling somewhat at some angle. Well, the way we do this in vector calculus is we use the formula work is force dotted with the displacement vectors. So the work vector dotted with the displacement vector. So it's a lot like what we talked about up here. Work is force times distance. Well, if we're dealing with vectors, work is force vector dotted with the displacement vector. So we're going to imagine that there's a vector here describing the displacement. So oftentimes we call our force F and our displacement R. So you'll see this formula as work equals F dot R. Okay, so if I know the components of my force vector, I can do this very easily. Suppose the components of the force vector were, let's say it's 4, 3. Okay, suppose we knew this. And that would, by the way, you could check this. It will have a magnitude of 5, right? You can check the magnitude. The displacement vector, we can see what it is. It's a horizontal vector, and its length is 10. So, and it's pointing to the right, so it must be 10, 0. Okay, so to compute the work here, what I would do is I would take my force vector and dot it with my displacement vector. And when I take this dot product, what do I get? I get 4 times 10 is 40. Plus 3 times 0. So that's just 40. And again, the units would be Newton meters or joules. Notice that the work is a little bit less this time. Before it was 50, now it's 40. Why is that? Well, we're computing how much work is done by this force. Well, not all of this force is pointing in the direction of the work. Only some of it is. Only that much of it is. And so of all this force that was applied, only some of it was doing the work. So actually less work was done in this scenario. Now in this problem, we were fortunate that we knew the components of the vector f. And if you know the components, this is a great way to do it. However, if you look at the problem that we started with here, we don't know that, right? We don't know the components of this vector. So we either need to find the components of this vector, which you could do because you do know the angle, or we could be a little bit more clever here, all right? If you remember the relationship between dot product and angle, then we can just use that, right? So remember, what we need to do is we need to take this force vector and we need to dot it with our displacement vector, right? So that's going to give us the work, right? So we're going to take force dotted with displacement. And then, like we were saying, there's a formula for this that relates it to the angle between the two vectors. Remember from the last video, this is the magnitude of the force vector times the magnitude of the displacement times the cosine of the angle between them. Well, look at this. They gave us the magnitude of the force. They told us it was 25. They gave us the magnitude of the displacement. It's 50 feet. Let me write down pounds here. We'll keep track of the... And they gave us the angle. That's theta. Cosine of 20 degrees. And so that's what we'll need to do to compute this. Okay? Well, if you compute all this out, you'll get 1,174.62 foot-pounds. Now, we're not using metric here, so instead of Newton meters, we have foot-pounds. They also call those slugs, although that's maybe less commonly done. Usually people just say foot-pounds, so I would probably just leave it like that. And that's how we can do a problem like this. So just keep in mind, there are several ways. Let me reappear here. There are several ways to do work computations depending on whether you know the components of the force vector or the angle between the force vector and the displacement vector. All right, that's it for this video.